is the mean arterial pressure, MEP? A lot of you selected A, average aortic pressure during the cardiac cycle. Option A is correct, but I really want to make sure because quite a few selected some other options too. So the mean arterial pressure we said was the systolic pressure divided by the diastolic pressure. And so we're looking at one vessel in particular. We're looking at the aorta and the pressures in that vessel. We're looking at that vessel during systole, where we've got the highest pressure during ejection, and then diastolic pressure is going to be the lowest pressure as the heart is filling. And so this is going to be in one specific vessel. So that eliminates option B, that eliminates option D, right? That talks about all arteries. And then we're looking at it during the entire cardiac cycle, right? So it's an average of the aortic pressure during the entire cardiac cycle. So the option here is, the correct option is A. All right, let's look at a few others. And just to clarify here, we haven't spoken about the word contractility, but it means how hard the heart is working. How much force are those cardiac myocytes producing, the force of contractility? All right, so let's look at the answers here. All right, so majority of you selected C, decreased arterial pressure, and the question was, which is not a factor that increases stroke volume? Now, when you think about stroke volume, you want to kind of pause and think about what that is. That's how much blood the heart is ejecting, right? How much is leaving the ventricle and making its way out into the artery. And so if you go through these one by one, we can kind of reason our way through this. So A, increased end diastolic volume. So if I increase how much volume the heart fills, I am going to increase how much the heart ejects. So A is going to increase stroke volume. So we're not looking at A. B, increased contractility. That's how hard the heart is working, right? If the heart is working harder, if those myocytes are producing more force, I'm also going to eject more blood. So that will increase my stroke volume, how much blood is leaving that chamber. So we're going to also eliminate B. C, decreased arterial pressure. Now, arterial pressure has to do with afterload. How much resistance is the blood that's leaving the ventricle trying to overcome in those arteries? And if we've got a lot of resistance, a lot of pressure in the distal arteries, we're going to increase how much blood can effectively leave that ventricle and move out into the arteries. So if I decrease my arterial pressure, I am going to increase my stroke volume. And so we're also going to eliminate C. Okay, I hope those three made sense. Now, when we get to heart rate, we know that the heart needs to spend adequate time filling in order to empty adequately. And so if I increase my heart rate, I'm going to actually cut down how much time the heart can spend adequately filling. And so if I can't fill adequately, I also likewise cannot empty adequately. Okay, and so if I increase heart rate, I'm actually going to decrease my stroke volume. Okay, so D is going to be the correct option here. All right, many of you selected, what was it, C? So that's not correct, but I really want you to understand why we kind of walked through how come heart rate is going to increase, and an increasing heart rate actually decreases how much time the heart can spend filling, and likewise how much it can eject. So that's going to decrease my stroke volume. So the correct option here would have been D. All right, let's look at one more and then we'll move along. I think these questions are really helpful so that you can see what types of application you should be able to do in terms of, let's see here. Okay, there we go. All right, last couple seconds. All right, let's take a look. Oh, so we've got kind of a tie for the most popular response, so B, C, and D. So what happens during isovolumetric contraction? So first thing, this is isovolumetric, and I really want you to understand what that word means. That means that all valves are closed. So anything that has a valve open, you can automatically eliminate. So we can eliminate option B, we can eliminate option C, right? Isovolumetric means that all 4 valves are closed. The volume is not changing, blood is not leaving any chamber. What we have is contraction, because this is isovolumetric contraction, of the ventricle. Okay, so that also eliminates A, right? The atria are not contracting. And so what we're left with is option D. So during isovolumetric contraction, remember when we speak about these phases, we're always referring to what's happening in the ventricle. So ventricle is contracting, building up that pressure in order to overcome the gradient that's needed, or create the gradient that's needed to open up the semilunar valves. And so as that pressure builds, both sets of valves are closed during that time. And so blood is neither leaving nor exiting that chamber. So the correct option here is going to be D. AV and semilunar valves are closed and ventricle is contracting. Okay, atria is not contracting and none of our valves are open. All right, and we could flip-flop this question and asked about isovolumetric relaxation. It would have been the same thing, but we would have had ventricles relaxing.